So, welcome to programming languages. Today we will just do a few elementary concepts, broad classifications of programming languages without going into too much detail. So, this is the first lecture, and so let's just look at the notion of a program or a programming language. So, we are all familiar with the notion of a machine, a computer, and it has what one would call a bare machine, has just a piece of hardware. It's usually in binary. Well, you can just think of it as a whole lot of switches connected with complicated circuitry. The memory, the arithmetic unit, all of them consist of switches activated one way or the other, and even in a and you can see it's going to be a big problem just operating those millions and millions of switches. Yeah. So what you have is a language which just consists of binary strings. So in a bare machine, what you would just have is a language consisting of binary strings. And so these binary strings in what is known as the von Neumann architecture, which is called the stored program concept, right? Both data and instructions have the same format, and so everything is a binary string, and depending upon how you look at it, it's either a data item or an instruction to execute something, right? So that is the von Neumann concept. So which means that programming such a machine basically requires you to be able to interpret certain sequences of bits either as data or as instructions, and if they are instructions, to manipulate some registers, maybe load into memory, store load from memory, store into memory, or perform some arithmetic operation or some logical operation, and so on and so forth. Right. So in general, even that language, what we might call the machine language, can be called a programming language, because let's take a very general view. What is a programming language? A programming language is just some notation for describing algorithms and data. So in general, we could consider a programming language to give you a means of representing algorithms and data structures. And when you have a representation of algorithms and data structures, presumably you are able to perform your manipulations. Yeah. So the first thing about a bare machine is that if you are going to use the machine language itself, then there is really no fundamental difference between the algorithm and the data, which means a sequence of instructions could just as well be regarded as data items. A sequence of data items, provided they have some circuitry, could also be executed as an algorithm. I mean, God forbid what might actually happen, but I mean in principle you could execute even a sequence of data items as instructions by interpreting it suitably, right. So the first distinction that we would like to draw is between what constitutes a data item and what constitutes an instruction. Okay, so there are various let's take a much more high level view. I mean, right now we are no longer in the 50s when the early machines came and you had to program in machine language or assembly language. So we will just look upon a programming language as just a notation for describing algorithms and data, and we could look at a program as just a sentence in this language, right. I mean, there's so it's a language like any other language, and it has certain rules, and you have certain what might be called well formed sentences, and a program is just some sentence of a programming language. A program is not necessarily an algorithm, well, simply because, I mean, you might have a well formed sentence which is not very meaningful. Okay, for example, the program could be a non terminating program, in which case it is no longer an algorithm. Okay. So important thing to realize is that an algorithm is a very abstract object. It does not have any concrete form. What is concrete is whatever is put down as a program. So the only concrete object that you can have is a program, and so the notion of an algorithm itself is an abstract is an abstract entity which requires a concrete representation in the form of a program. And if a program is a sentence in the programming language, then what you require really is a programming language. And another alternative way of looking at the notion of a program vis-a-vis a programming language is as we might think of a program as a specification of a computation. We might think of a program as a specification of a computation, which means we have some notion of what constitutes a primitive step of the computation, and the program gives you a finite representation of possibly an infinite sequence of steps in a computation process. Yeah. So the emphasis in all these cases is in the nature of a finitary specification. Okay. I mean, you should have a program should be a finite object by itself. A programming language itself is not a finite object, because there are an infinite number of programs that are possible. But each program itself is a finite object, because it is just a sentence of the programming language. Yeah. And then we might think of a programming language, if you look upon a computation and the steps in a computation as the most basic feature, then you might think of a programming language just as some notation for writing programs. And in all this case, we should emphasize the fact that this notation is important, because our notation is to give you a finitary specification of possibly an infinite object, right. So we might emphasize that this is actually a finitary specification. Yeah. And these programs themselves as concrete objects are finitary, but their effects could be infinitary, right. So the moment you are trying to represent any infinitary object in a finite manner, you require and it has to be machine understandable, you require certain rules. Okay. So well, so let's look at this process of essentially giving a finitary representation to what you might consider infinitary objects. Okay. So what kinds of infinitary objects are we normally concerned with? Well, in the most general case, an algorithm is what you want to represent in a program, and an algorithm really, in the most general case, is a function from some domain to some codomain. And a function need not necessarily be finitary, because the domain could be infinite, the codomain could be infinite, and so we might think of an algorithm in general as computing either a function or a relation, a method for computing some mathematical function or relation, and these functions and relations could be infinitary. Yeah. So and so we are looking at infinitary objects, basically mathematical functions. Relations can also be considered functions. Okay, all relations could be considered functions. So in general we will concentrate on trying to get finitary representations of infinitary objects, and these infinitary objects are really functions. So you can think of the whole study of programming or computation as trying to compute or trying to give finite specifications of computational steps of abstract mathematical functions. Yeah. So however, when you look at so if you look at mathematics itself, it has a fairly rigorous notation. So you could think of mathematics itself as a sort of a programming language, except that it has one important drawback, that is that it does not specify what are the primitive computations that are possible within the mathematical language. Okay. So when you normally when you are talking about an algorithm to compute some function, what you have implicitly defined is a set of primitive functions or primitive computation steps in terms of which you are going to express this algorithm. Okay. So one obvious case in which a lot of mathematics is not, it does not fit into the general framework of a programming language is this, for example, the representation of infinite sets. Okay. So if you look at, I mean, whatever you must have studied in school and so on, if you look at infinite sets, well, the standard thing in school is to say that you can either represent a set in roster form or in set builder form. Is that, yeah? So a roster form just means enumerating a list of elements, and a set builder form essentially means giving an abstract, giving a predicate which the elements of the set should satisfy. Okay. So the main difference between the roster form and the set builder form, the set builder form is also called definition by abstraction. Okay. So the main difference between the two really comes up for infinite sets. So in the case of infinite sets, what you normally do is, so supposing you want to specify the set of even numbers, so you open braces, you write maybe 0, or if you do not include 0 then you write 2, comma 4, comma 6, comma and then dot dot dot. I mean that's, so that is where the inadequacy of mathematical notation comes. Okay. Simply because you are not interested really in any underlying computational process. As far as mathematics is concerned, a large part of it is just the existence is more important than a computational method. Okay. And whereas the set builder notation or the definition by abstraction gives you a finitary specification. So you can represent the set of even numbers through a notation which consists of a braces, which consists of a bound variable, okay, a definition, a bound variable and a predicate in terms of the bound variable. Okay. So a typical definition of, let us say, even numbers would look something like this. You would say it is 2x where x, let us say, belongs to the natural numbers, right. So here if you look at x, x is like a locally declared variable. Okay. In fact, this is a sort of declaration of x, and this 2x is a property that the elements of this set should satisfy. Now here is a case of a finite tree specification as opposed to this infinite tree specification, right. Yeah. In fact, this is a finite tree specification in more ways than one. Firstly, this represents a logical predicate expressed in first order logic in a finite sentence of the first order logic, okay. And this, so you might consider this as a succinct finite tree specification of essentially an infinite tree object, the even numbers, whereas this is really open to many, this is really ambiguous in the sense that it is not at all clear from this enumeration what should be the next one. I mean, you are implicitly using human intelligence and human understanding to the human ability to perform induction to claim that the next number would be 8, but I am not at all sure that the next number should be 8. There might be other patterns, for example, okay, it might satisfy other predicates, whereas this is what one might call an accurate succinct finite tree representation using just the language of first order logic built up on a single predicate, a single binary predicate on sets, right. The binary predicate is this belongs to, yeah, okay. So a lot of a lot of what we are going to do is also going to be related to the language of logic in some ways. You will see the analogies between programming languages and logic as we go along. The main motivations of logic are really of a slightly more abstract nature, but programming languages derive mainly from logic, yeah, in the sense that a language like first order logic does not allow you the freedom to write these dots. I mean, there is no such thing, okay. You have a method of construction of predicates which is always finitary. You have rules of inference in logic which are always finitary, or they might be infinitary, like if you have axiom schemas, if you have rules like modus ponens, they are finitary representations again of infinitary objects, okay. Further, in a logical language with axioms and rules of inference, there is implicitly understood that those rules and axioms and rules of inference are such that there exists an algorithm which, given any instance of the hypothesis of these rules, should be able to tell you whether the conclusion of the rule is a valid inference, yeah. So if you were to take a simple logical rule like let us take modus ponens, what you have is I will write this. So you have a predicate x, you have a predicate x arrow y, and you have y, okay. So this x and y are, so this rule actually specifies a a pair of this form, right. where x and y are belong to I do not know, let us say the language of first order logic, which I will write L1 as opposed to propositional logic, which I will write L0. Okay. So, L1 is let us say first order logic. So, what you are saying is you take two sentences of first order logic, and if they have this pattern, that call one sentence x and the other sentence has the pattern x conditional y, then you are able to infer y, and you cannot have all rules of inference in logic are finitary, they are also finitary specifications. Yeah, and something that is absolutely essential is that it is decidable by an algorithm whether a certain step in the proof of a logical statement was derived by an application of a rule of inference on some preceding steps. Okay. So, which means that if you claim that you have some predicates you have some predicates of the form let us say A arrow, B arrow, not C, where let me put brackets here, and you have something like A arrow B, and then you derive from these premises, if you were to claim that by the use of modus ponens you can infer not C, then there has to be an algorithm which, given these two as input, will be able to tell you whether this is an instance of an application of this rule of inference. Okay. In this case, the algorithm should actually tell you that it is not an application of this rule of inference. Okay. In other case, so it should be able to give you both yes and no answers in finite time. Okay. So, most programming languages that we will study will have a lot of their motivations actually derived from logic. A large part of logic was actually concerned with the notion of how much of mathematics is actually doable by a machine. What kinds of proofs what kinds of theorems in mathematics can be actually proved by algorithms, by a machine whose basic primitive by machines whose primitive operations are that they are able to do pattern matching and substitution. Okay. So, this is an instance of doing pattern matching and substitution. An inference rule is really an infinite object, it is a relation of this kind with a finite representation. A proof is a finite object, a theorem is a finite, a theorem itself is a sentence of a logical language and is a finite object representing possibly an infinite number of instances. Okay. So, the finitary nature of all these will actually influence the nature of a logic. So, for example, you cannot give axioms and rules of inference which are infinitary in a logical language. Okay. So, everything that is infinitary should have a finite representation. There are of course infinitary objects which will have no finite representation. They are clearly not going to be part of our computational process. Okay. So, for example, generating an infinite sequence of random numbers, by random numbers I do not mean pseudo random numbers, I mean pure random numbers, is, well, it is not a computational process, period. So, we are interested in those kinds of infinitary objects which somehow have finitary representations. Yeah. So, like maybe infinite sets represented as predicates, unary, binary, ternary, but some finitary, with a finite tree representation. We are interested in infinite tree computational processes which have finite tree representations. We are interested in programming languages which allow for finite tree representations of inherently infinite objects, infinite tree objects. Yeah. So let's go ahead with. I mean, this much of philosophy is perhaps sufficient for the moment, but it's important to realize that right from 1900, when the mathematician David Hilbert posed this problem to the Congress of Mathematics, the main emphasis of logicians and computer scientists has, or rather computer scientists came very late in the game, but logicians mainly, has been to try to define the notion of an algorithm, to define the notion of a computational process, to be able to exactly define what is possible by a computational process, what is not possible by a computational process. Everything that is possible by a computational process should have a finite representation, and anything that is infinite tree is not part of the computational process with some restrictions. Yeah. So if you just come down from logic a bit, then what we are looking at, so we can look at a logical language itself as a mathematical object. For example, there exists only a finite number of rules for generating an infinite number of sentences of that language. Okay. So you take a language like first order logic, you have only a finite set of formation rules which allow you to generate an infinite number of logical sentences. Okay. And that the finitely nature of the rules also gives you an algorithm to check, given a string of symbols, whether this string of symbols is a syntactically valid sentence of the logical language. Yeah. So an important element of that logical language is that the generation process should be finite, should be finitary. There should be only a finite set of rules, and there should be an algorithm which will check, which can clearly tell you whether a given sentence is a well formed sentence of the language, right. And if you look at propositional logic, it does not allow you to specify, for example, infinitary objects like for which you require, if you were to actually apply propositional logic to some area of mathematics like set theory or number theory, what you see is that it allows you, it does not allow you to specify infinite sets easily, okay, or certain properties of infinite sets. So very often, so an extension of propositional logic which allows you to do this in a finitary way is the use of quantifiers and the extension of propositional logic to first order logic. Okay. So you can, for example, specify the whole of set theory in first order logic. I mean, the axioms of set theory, the predicates that are valid for all possible sets which do not, I mean by set theory I mean axiomatic set theory in the sense that we do not assume numbers or we do not assume any predefined set of objects. The only notion is the notion of a set. Okay. So you generate all sets, you generate numbers, everything from the notion of an empty set and a single binary predicate called belongs to. Yeah. So and they have these formation rules and so on and so forth. So anyway, so we are interested essentially in capturing infinite tree processes within finite tree languages. Yeah. So so we might, so let us, so and the main way, the main difference between, so you can see a progression of ideas. Firstly, there is pure mathematics, which is Platonic in nature, in the sense that the notion of a computation itself is not important, it is not an important element of the formal discipline of mathematics. Then you have logic, which actually gives you a loose notion of what is possible by a machine and what is not possible, and allows you to specify infinitary objects in some finite ways. And lastly, we have programming languages which specify with a great deal of accuracy exactly the primitive computational processes that you are allowed to use. Okay. And so a programming language is also has to satisfy all the constraints of a logical language, and in addition it should be consistent with what might be called the primitive computational processes. Okay. For example, one primitive computational process that you must have all studied in school is that of ruler and compass constructions. Yeah, ruler and compass constructions. Okay. Yeah. So one, so there are only two primitive computational steps. You are able to draw lines with a ruler, mark off segments. You are able to use a compass to draw certain angles or to draw arbitrary angles. Okay. So one impossible computation in this case is there an algorithm using only these primitive concepts to trisect an arbitrary angle? Okay. For example, you are not allowed the use of protractors and so on, you are not allowed to measure the angle. You can only prove that an angle is of a certain measure. For example, if you draw a line perpendicular to another line with a construction proof which shows that it is perpendicular, and then you bisect that, then you can claim that the bisected angle is, let us say, 45 degrees. But given just an arbitrary angle, 2 rays from a point, to be able to trisect it with just these primitive tools, for example, is an impossible task. Okay. So you might think of the algorithms of ruler and compass constructions, the algorithms are, it's a programming language in which you have only these two computational processes, if you like. It's not machine readable, it's meant to be human readable. So you write it in a loose fashion, but essentially you use only those computations which are possible within the domain of Euclidean geometry, which means you are not allowed to measure out angles yourself, you are only allowed to prove that a certain angle has a certain measure. You are not allowed to measure out lengths in terms of centimeters or meters or whatever. You are only allowed to measure out an arbitrary unit and take multiples of that arbitrary unit. You could bisect that arbitrary unit, you could trisect that arbitrary unit of length measure, okay, and so therefore claim that it is that it's actually 1/3 of the unit that you took. But for example, you can't claim that you have constructed 1/pi of a unit of length unless you can prove that just by this process you are going to get something that is 1/pi of the unit. Yeah. Anyway, so our programming language has ingrained in it the normal computation processes that we associate with a digital computer. That's not the last word. You could have other computational processes such as ruler and compass constructions, you could have analog computers and so on and so forth, but we are interested excuse me, we are interested primarily in the computation processes associated with digital computers. Yeah. So, what we have are as I said, we could look at we could look at even the machine language as a programming language, but we are not really interested in a machine language because it is a very simple sort of a language, very difficult to get any program right, I agree, but the language itself is a very simple language, okay, and probably that is why it makes it so difficult to program. And what we are interested in primarily are what are known as high level languages, where the primitives of the computation process of the primitives of computation, or what you might say is the machine that is made available. So, once you have implemented a language on a machine, you could think of that as a machine of that language. So, supposing you have implemented, so most of you have done some programming in Pascal. So, at that point when you are doing Pascal programming, you are not really worried about the underlying machine language, the underlying architecture, you are not worried about anything. As far as you are concerned, what you have is a Pascal machine. Okay. So, there is a level of abstraction at which you can consider that you have built, so to you it makes really no difference whether that Pascal machine, whether Pascal is the hardware machine language of that machine, or is it, or it is just some software language. As far as you are concerned, it is a Pascal machine. Okay. So, it is important to realize that you can actually take some bare machine and cover it up with layers and layers of software and think of just one abstract machine which gives you certain capabilities. So, if you look at the bare machine, it gives you only the capabilities to manipulate switches, to write programs in binary and so on. If you look at a Pascal machine, it gives you no extra computational power, but it gives you the ability to look upon the whole thing as a single machine, which allows, let us say, construction of complicated structured programs. It allows various kinds of abstraction mechanisms, procedures, functions, and it allows you to express in terms, I mean it allows you to express things differently, okay, from what the bare machine would have given you, right. So, let us look at why we should study programming languages, because all the time we are looking at the construction of some virtual machine, and what facilities, we are not really interested in the facilities that the machine gives us, we are interested in various in what kinds of features are there in that machine. In the case of a bare machine, you are interested in its architecture. Now, if you have a Pascal machine, its architecture is really the features of Pascal. Okay. If you have a Lisp machine, its architecture is really the features of Lisp, right. So, our study of programming languages is mainly to, for example, you want to understand why certain features have been included in the programming language. You want to understand, for example, how best those features could be used. Okay. And if you also want to understand how that language is implemented, okay, so that presumably you would be able to, with all this understanding, presumably you would be able to learn new languages easily, maybe you can design new languages, that is more important, and perhaps you would also be able to, if you understand the underlying implementations, maybe you would be able to incorporate new features in a programming language. Yeah. So let's just look at languages. Let's sort of classify what kinds of languages there are. Firstly, we have these low level languages, which are machine and assembly language, which are not of interest. I mean, you will learn about them in some course on architecture or organization, but what we are interested primarily are these high level languages, okay, of which we can think of three broad classifications. One is a class of imperative languages, in which most of the last 40 years has gone in, since the first digital computers, has gone in the design of imperative languages. Then there are what are known as functional or applicative languages, and then it is possible to use logic itself as a programming language. Yeah. And then what you can do is you can actually mix up all these things, and for example you can have impure functional languages. Okay. An imperative language means that it uses the notion of a command, it uses the notion of a state to change a state. So, the commands change states, that is what an imperative language would be. Okay. So, a functional language is one which allows you to program in something that is as close to mathematics as possible. No? Okay, we'll get into these notions a bit more in detail later. Okay, so a broad classification of languages is just in terms of high level languages: imperative, functional, logic. You could also classify languages by features, and by features in the sense that what is the most glaring feature in the language. Well, so a large part of our languages are really what might be called sequential languages. Yeah. So, most of the languages that you are programmed in are really sequential languages. Then you have what are these parallel languages, which are very often languages meant for certain specialized architectures, like you have a single instruction, multiple data, and you execute things in parallel. I mean, there are implicit methods to do things in a parallel fashion. You have what are known as distributed languages, in which they are not. So, in the case of a parallel language, you assume that there is you assume that there are so many processors which will all execute the same instructions in a synchronous lockstep fashion. Okay. So, most of the vector processors actually have sequential languages vectorized or made parallel, like in the case of Fortran 90 or vector processing Fortran, and so on and so forth. Yeah. Distributed languages are those in which you actually assume that the different units of a program are going to lie geographically distributed across, let us say, a network, and they have to somehow cooperate to achieve maybe some common task, right. Then you have these. So, in both these cases, we might loosely assume in both parallel and distributed languages that the notion of a process, of a computational process into which a program is split, is inherently or intimately related to really the computational power, to the number of units of computation, that number of units of let us say CPUs that you have. I mean, so the notion of a process and a processor are really the same. I mean, you are writing one process per processor in both these cases maybe. Yeah. In the case of concurrent languages, what you are basically taking the notion of a process to be a loose entity completely different from, it does not necessarily have to be mapped on to the existing processors. The notion of a process gets delinked from the notion of a processor. Then you have other kinds of languages, those whose primary feature is that of modules, separate compilation, and more recently you have what might be called object oriented languages. These add extra features on top of existing languages usually, but there is something fundamental about the new feature that they introduce. Yeah. So when we look at so let's just quickly go through, for example, some of these languages. So if you were to take the history of programming languages, you would find that there is a certain chronological dependence, right. So the first high level languages, so to speak, were Fortran, which is mainly meant for scientific computation, and then COBOL, which is meant for business. It was more verbose, it actually used full English sentences to represent computations. It made the first distinction between data and program, and was meant to use a large amount of data and do very low processing. I mean, it was IO bound programs, whereas Fortran was meant for minimal IO and maximal computation. Yeah. And these languages gave rise to one important class of languages called the Algol like languages, which came from the report from the Algol 60 report. Fortran also had its offshoots in BASIC. Then there were these among the Algol like languages. Among the Algol like languages, you have Pascal, PL1, similar. PL1 was an attempt at a unified language for both scientific and business commercial processing, and from Pascal you get extra features in something like Modula and Ada. From Simula you got these object oriented languages starting from Smalltalk 80. Okay, and all these, and somewhere in a parallel stream which is marked by this orange, you have BCPL and C. Actually BCPL was a transformation of a language called B, which itself was a transformation of a language called A, and the C was derived from BCPL by modification. Yeah, and then once Smalltalk 80 came up and C was there and object orientedness became a big buzzword, you had C++, yeah, which is not here. Okay, so so that is briefly what we are, you might say our pedigree of languages is mainly. Oh, we also have these functional languages, right? So let's look at functional languages. So you have apart from these imperative languages, you had basically the first functional language was Lisp, from which were derived various versions, MacLisp, Scheme, Common Lisp. MacLisp and Common Lisp are really impure versions of Lisp. When we understand functionality, we will come to what they mean, impure versions. But many of you have probably studied Scheme. Okay, it's a cleaned up version of Lisp, and in parallel with Lisp, which is meant for list processing, there was also a language designed in the 60s called Snowball, which was meant for string processing, which allowed efficient pattern matching constructs to be programmed, and these have actually yielded, along with the emphasis on type checking, to a language called ML, which came up in the 80s. And actually all these languages, Lisp and ML, were all inspired by the what is known as the lambda calculus, which we will study, which is the basis of all functional languages. Okay.